Calibration Curves, the unsung heroes of biomedical sensors, written by Bill Nye from the Public Broadcasting Service. Have you ever wondered how biomedical sensors measure vital signs accurately? These devices are integral to modern healthcare, providing critical data that can save lives. From monitoring blood glucose levels to tracking heart rhythms, these devices rely on a critical process called calibration. Calibration ensures that the readings are precise and trustworthy. Imagine a world without accurate measurements. Medical diagnoses would be unreliable, and treatments could be ineffective. The consequences could be dire, leading to misdiagnoses and improper treatments. This is where calibration curves step in as the unsung heroes, ensuring the accuracy and reliability of biomedical sensors. They are the backbone of precise medical data. Calibration curves are like the instruction manuals for biomedical sensors. They guide the sensors to interpret raw data correctly. They provide a roadmap for translating the raw data collected by sensors into meaningful medical information. This transformation is crucial for accurate patient monitoring and diagnosis. Just like you wouldn't trust a clock that shows the wrong time, you wouldn't want to rely on a medical sensor that hasn't been calibrated. The stakes are simply too high. In this essay, we'll delve into the fascinating world of calibration curves, exploring their importance, creation process, and real-world applications in biomedical engineering. Join us as we uncover the meticulous work that goes into making these sensors reliable and indispensable in healthcare. Sensors, translating biology into electrical signals. Biomedical sensors are remarkable devices that act as our eyes and ears inside the human body. They convert biological parameters like blood pressure, oxygen saturation, and electrical activity into measurable electrical signals. For example, a glucose sensor measures the electrical current generated by a chemical reaction involving glucose in the blood. However, the raw electrical signals produced by sensors are often not directly proportional to the actual biological parameter being measured. This is where calibration comes in. Calibration is the process of establishing a relationship between the sensor's output signal and the corresponding values of the biological parameter. This relationship is represented graphically by a calibration curve. Building trust, the art of creating calibration curves. Creating a calibration curve is like teaching a sensor to speak the language of the biological parameter it's measuring. This involves exposing the sensor to a series of known standard solutions or stimuli. These standards serve as benchmarks, providing known values of the parameter being measured. As the sensor is exposed to each standard, its output signal is carefully recorded. This data is then plotted on a graph with the standard values on the x-axis and the corresponding sensor output values on the y-axis. By connecting these data points, we obtain the calibration curve, which represents the unique relationship between the sensor's output and the actual biological parameter. Precision matters. Why calibration is non-negotiable. Accurate calibration is paramount for reliable sensor readings. Without proper calibration, the sensor's output would be meaningless, leading to inaccurate medical diagnoses and potentially harmful treatment decisions. Imagine a blood glucose monitor that hasn't been calibrated correctly. It could display dangerously low or high blood sugar levels, even if the actual levels are within a healthy range. Calibration ensures that the sensor's output accurately reflects the true value of the biological parameter. By establishing a precise relationship between the sensor's signal and the parameter, calibration allows us to trust the readings and make informed medical decisions based on accurate data. Sensor drift. The case for regular recalibration. Biomedical sensors are not immune to the passage of time. Like any other instrument, they can experience wear and tear, environmental exposure, and other factors that can cause their performance to drift over time. This means that the relationship between the sensor's output and the biological parameter it's measuring can change, leading to inaccurate readings. Regular recalibration is essential to combat sensor drift and maintain the accuracy of biomedical sensors. Recalibration involves repeating the calibration process at regular intervals using fresh standards to adjust for any changes in the sensor's response. The frequency of recalibration depends on the specific sensor, its intended use, and the manufacturer's recommendations. Calibration curves in action, from glucose monitoring to heart health. Calibration curves are the invisible force behind countless biomedical applications, ensuring the accuracy and reliability of medical devices we rely on every day. These curves are mathematical tools that help translate raw data into meaningful information, making them indispensable in the medical field. Let's explore two examples where calibration plays a critical role. Glucose monitors and electrocardiogram, ECG machines. 1. Glucose monitors. For people with diabetes, accurate blood glucose monitoring is crucial for managing their condition and making informed decisions about insulin dosage and meals. Without precise readings, managing diabetes effectively becomes a challenge, potentially leading to severe health complications. Glucose meters rely on calibration curves to convert the electrical signals from test strips into blood glucose readings. These curves ensure that the readings are accurate and reliable, providing users with the confidence they need to manage their health. These meters are typically calibrated at the factory using standard glucose solutions, and users may need to recalibrate them periodically using test strips provided by the manufacturer. This periodic recalibration is essential to maintain the accuracy of the device over time. 2. Electrocardiogram, ECG machines. ECG machines, which record the electrical activity of the heart, are essential tools for diagnosing heart conditions such as arrhythmias, heart attacks, and heart blocks. These machines provide critical data that can be life-saving. ECG machines use electrodes placed on the patient's chest to detect the tiny electrical signals produced by the heart. These signals are then amplified and filtered to create a clear and accurate representation of the heart's activity. Calibration curves ensure that the ECG machine's amplifiers and filters are working correctly, and that the recorded signals accurately reflect the heart's electrical activity. This accuracy is vital for diagnosing and treating heart conditions effectively. Regular calibration of ECG machines is crucial for obtaining reliable diagnoses and making life-saving treatment decisions. Without regular calibration, the risk of misdiagnosis increases, potentially leading to inappropriate or delayed treatment. Hands-on calibration, plotting your own curve. Now that we've explored the importance of calibration curves, let's try a simple exercise to solidify our understanding. Calibration curves are essential in ensuring the accuracy and reliability of sensor measurements. Imagine you're working with a sensor that measures temperature. This sensor is crucial in various applications, from medical devices to environmental monitoring. You expose the sensor to known temperatures in Celsius and record the corresponding sensor output voltage. This process helps in creating a reference for future measurements. Sample data, temperature in Celsius, 10. Sensor output voltage, 1.0. This is your first data point, temperature in Celsius. 20. Sensor output voltage, 2.1. Notice the increase in voltage as the temperature rises. Temperature in Celsius. 30. Sensor output voltage, 3.0. The relationship between temperature and voltage becomes clearer. Temperature in Celsius. 40. Sensor output voltage, 4.2. This data point continues the trend. Temperature in Celsius. 50. Sensor output voltage, 5.1. Exercise 1. Plot the above data on a graph paper or using a spreadsheet program. This visual representation helps in understanding the data better. 2. Label the x-axis as temperature in Celsius and the y-axis as sensor output voltage. Proper labeling is crucial for clarity. 3. Draw a smooth curve that best fits the plotted data points. This is your calibration curve. It should reflect the trend observed in your data. Questions. 1. What is the sensor output voltage when the temperature is 25 degrees Celsius? Use your curve to estimate this value. 2. What is the temperature when the sensor output voltage is 3.5 volts? This requires interpreting the curve in reverse. This simple exercise illustrates the fundamental principle behind calibration curves, establishing a relationship between a sensor's output and the parameter it's measuring. By understanding and applying these principles, you can ensure accurate and reliable measurements in your work. The importance of calibration, ensuring accuracy in biomedical engineering. Calibration curves are the unsung heroes of biomedical sensors, ensuring accurate and reliable measurements that are crucial for medical diagnoses, treatment decisions, and monitoring patient health. By understanding the importance of calibration, the process of creating calibration curves, and their real-world applications, biomedical engineers can develop and deploy medical devices that improve patient care and advance the field of healthcare. Remember, accurate measurements are the foundation of sound medical practice, and calibration curves are the key to unlocking this accuracy.